Distortion. I know you've heard that term before, but what does it mean? What does it sound like? That's what we're going to talk about in today's video. In order to keep this video short, I'm going to try to keep things very concise and to the point. There are three main types of distortion: harmonic distortion, intermodulated distortion, multitone distortion. And in this video, what I'm going to try to do my best at is to provide you with real-time measurements synced up with audio of those measurements. So what we've got here is the entire measurement setup and listening setup. We've got the speaker, which is speaker X. Now I may block this out because I don't want people focusing on the speaker. I want them focusing on the content of this video. We've got my measurement microphone, and then we've got my voice microphone. Now normally the voice microphone would not be out here. It's only out here for my testing. We normally have the test microphone only, which runs through the Klippel near-field scanner, out the bottom, and then runs into the Klippel distortion analyzer, which is tied into my computer, which is tied into the Klippel software. And depending on what module or what test I'm trying to run at the time, the software knows what to do with the stimulus collected from the microphone, and then it will report that to me on the screen. What I'm going to do in this video is I'm going to actually be recording the stimulus sent out from the speaker, captured by the measurement microphone, as well as captured by the voice microphone. Now this voice microphone is connected to my computer that's inside. So what I'm going to be doing is collecting audio from the test while I'm also grabbing a screenshot of the measurement process. And for each one, I'm going to talk to you about what the measurements are showing you as it's being conducted, or maybe after, depending on how hard this whole video is to put together. As part of all of this testing, you're going to be listening to a tone or a series of tones, depending on what the test is, which I'm going to cover in a second. Now that tone or series of tones is going to be swept at different volumes. First volume is going to be 70 dB at 1 meter, and then the last volume is going to be 96 dB at 1 meter. And we're going to step in 4 increments. So we're going to go roughly 70 to 78 to 86 to 96. And yes, I know 86 to 96 isn't the same step, but it's like 8.5 dB in between. I'm not going to do that math in my head and look like a fool in real time because I can't math. But regardless of that, that's what the video is going to be showing you, and that's what you're going to hear. Now for each test, so the harmonic distortion, IMD, multitone test, I'm going to play different tones, right? And I'll explain to you what those tones are going to be before I start each test. But just understand up front that you're going to hear 4 different volume levels for each test that I'm doing. I'll also suggest that you wear headphones for this test, because while you can hear the differences through your phone, through your PC speakers, through your loudspeakers in your listening room, TV speakers, whatever, you can hear the difference. Hearing the difference on headphones is much, much easier. And also with that said, since I'm going to be playing test tones, what I'd suggest you do is before I play each test, before I start each test, turn the volume down. So start at a low volume. Now, the flip side of that is when the first tone plays, it's going to be at that 70 dB volume, so it's not going to sound as loud. But you can play around with the volume. You can restart the test when you figure out what's too loud. What I don't want you to do is to have headphones on and have your volume cranked up, and then that first tone comes in or that last tone comes in and it just blows your ears off. So I warn you again, start with the volume low before each test. I'll throw up a graphic to warn you. I'll give you 5 seconds to turn the volume down. Make sure you do that, and then you can go back and listen at different volumes as you need to. Now, for what it's worth, I did all this testing one round earlier to make sure that I'm not going to run into distortion for the voice microphone where it is. And on my Motu M2, the volume bars that give me an idea of where the signal level is, it's always green, so it never even hits yellow. So no issues with the voice microphone at all. And then this measurement microphone can take a lot of SPL before it runs into issues. But at the same time, I don't want it too far away, because if I have it much further away, then I'm going to capture a lot of the room environment, and you're going to hear some of the room from the voice microphone. But just understand that normally this isn't how I conduct my test. This is just set up for this video. I want to state that right up front. The first test is going to be the harmonic distortion test. The harmonic distortion test is just a test of one tone at a time, and then it picks up the harmonics created by that tone. So you can have a tone of 100 hertz, and then the next harmonic of that is 200 hertz, and then 300 hertz, 400 hertz, 500 hertz, so on and so forth. Meaning that the fundamental tone, 100 hertz, has a second order harmonic, 2 times 100, 200 hertz. Has a third order harmonic, 3 times 100, the fundamental, 300 hertz, okay? I don't know why I just did that either. That was really weird. The fourth order harmonic is going to be 4 times the fundamental, which is 100. So that's going to be 400 hertz, then 500 hertz, 600 hertz, so on and so forth. That's how you get the harmonics of the fundamental test tone. Now, in my opinion, hearing harmonic distortion, I just don't think that we have the ear for that. Now, I know some people say that they can hear harmonic distortion, and I think to a degree they can hear distortion, or they can, I should say, I think they can hear distortion, but I don't think that they can singularly say it's harmonic distortion, because when you listen to music, you're listening to a lot of different tones at one time. You're not listening to one tone, which again, remember, harmonic distortion. And we're going to touch on that in a subsequent set of sweeps, and you'll see what I mean when we get to that point. But for right now, let's focus on the harmonic distortion. So what I'm going to do is I'm going to play one tone at a time from 400 hertz to 6 kilohertz. And the reason I chose that band is because I wanted to focus on the voice region, because it's easier to pick up distortions through that region, and plus it'll save us some time. Normally, we also will typically run the harmonic distortion as a sweep, so it'll sound like whoop, and you probably heard that before. But for the purpose of this video, it's going to be harder to pick out the individual tones, so that's why I'm doing individual tones. There's going to be 20 steps from 400 hertz to 6 kilohertz. It's going to take a little bit of time. Give it time. Remember, wear your headphones, but also remember, go ahead and turn your volume down. You can always turn it back up and start this section over again if you want to. Play it safe, turn the volume down, don't blast your ears off, and here we go. First of all, I want to state that up here are the different voltage levels that represent the output volume. 1.13 volts is fed to the speaker. That results in about 70 dB at 1 meter. 3.06 volts is about 78 dB. This is about 86, 87 dB. And then this is about 96 dB, all again at 1 meter. When the tones play, you're going to hear this voltage, this voltage, this voltage, then this voltage in that order. So it's going to sound like boo, 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 boo. It's just going to keep ramping up in volume. When those distortion components are recorded, they'll be displayed on the screen. So it's going to take a little bit of a second for them to display. There's a little bit of a lag. Up here in the top left is the total harmonic distortion. Y-axis is 0 to 10%. This is in percent. Second harmonic distortion is over here. Third harmonic distortion is down here. And then this is going to show you in real time the tone that's playing and the voltage that is playing. And then once I get through playing all of these, we'll come back, we'll discuss this a little bit. Let's talk about the results. What we can see is the total harmonic distortion is about 1% for the most part, from 70 dB to about 87 or 88 dB, except for 400 hertz to 1 kilohertz at the high output volume, 96 dB, relatively high. I mean, it's above 3%. So that's interesting. We can see that something certainly breaks down between about 88 to 96 dB. What makes that distortion component so high? Well, we can see if we look over here at the second order harmonic distortion, it's right here. So when 400 hertz is played, it's going to sound more like 800 hertz. And when 1 kilohertz is played, it's going to sound more like 2 kilohertz at this output level than it does at the lower output levels. As compared to the third order harmonic distortion, where all of this is below roughly 0.5%,
So more than likely, if you do hear distortion artifacts, it's going to be born from the second order distortion. And given that the second order distortion is so close to the fundamental, it is likely to be masked, meaning that it's going to be covered up by the fundamental tone because it's still relatively low in level. At 3%, it's about 30 dB down. Now, depending on the music you're listening to and depending on how good your ear is, you may or may not hear this distortion. And I'll be honest with you, in this particular test, I didn't hear this distortion.
If harmonic distortion is one tone at a time, then intermodulated distortion, which is what we're talking about right now, is two tones at a time. Meaning that normally what you do is you fix a bass tone, and in this particular case, I'm going to be playing 50 hertz. What I'm also going to do is play a sweep of voice tones. Those voice tones are going to be 400 hertz to 6 kilohertz in 20 different steps, just the same as it was for the harmonic distortion. So the difference here between IMD and HD testing is going to be, now with IMD testing, I'm adding that 50 hertz fundamental tone. Now what you're going to hear is at lower volumes, it'll probably sound okay. You're going to hear basically just the two tones playing at one time. But as I increase the volume higher and higher through those 4 different steps, you're going to hear some weirdness. You're going to hear probably what sounds like, maybe best described as a warble sound. It's going to sound weird. That's intermodulated distortion. And that's created by playing a fundamental tone at a lower frequency and then higher frequencies. Now you can also do this the other way around. Intermodulated distortion can be any set of two tones, but that's what I'm playing right now. 50 hertz and then sweeping a bunch of different tones through the voice region. Listen for how those tones sound different as I increase the volume. And what you're going to be picking up on most likely is going to be the amplitude modulation. There is Doppler distortion, which is caused by phase or timing differences. When you have a small driver and it's moving a lot of excursion, like one way, then that creates Doppler distortion. But you're not going to hear Doppler distortion. You're going to be hearing amplitude modulation. And for what it's worth, I made a post on my Facebook group overnight, last night, and then Lars Riesbo from Purify replied back. Now, my understanding of what I was hearing, I thought it was Doppler distortion. This is just me being completely candid because I don't know everything. I try to do the best I can with trying to help people understand and trying to teach. I'm still learning continually, and I think this is a great opportunity for us all to learn. So that's why I'm telling you this, okay? So Lars posted a link basically saying, hey, Erin, you think it's Doppler, but it's really amplitude modulation. And it turns out that you hear amplitude modulation. Klippel has a white paper on this. I'll try to link it in the description below. So in the particular case of this speaker, yes, indeed, I'm hearing amplitude modulation. And in the data that we're going to see in real time, you're going to see that it's dominated by amplitude modulated distortion. There's also a lot of Doppler distortion, but you're not going to be hearing that. You're going to be hearing the amplitude modulation because it is much more dominant than Doppler distortion. And I'll put the link below because they have a really good link on the Purify website to show you the difference of those two by themselves, because there's no way for me to separate those two different contributions, amplitude modulation and frequency modulation, aka Doppler distortion. I can't separate that in this particular test, but they've done a really good job of doing that on their website. I'll link that below. You can follow that. So yes, put your headphones on, turn your volume down. Let's kick off the IMD test.
Before I let this play all the way through, I want to point out a couple things real fast. The second order distortion is up here and the third order distortion is down here. But mainly note that I've had to change the scale from 0% to 100% rather than 0 to 10% like you saw with the harmonic distortion. The reason for that is you're about to see some of these numbers jump drastically, especially when you get to around 2 kilohertz. Listen for how that third voltage and that fourth voltage sound. It'll almost sound like, to me, it reminds me of like a bird whistling. The pitch of the frequency changes so much. And remember, what we're doing in this test is we're playing a 50 hertz tone down here, but we're recording the voice tones up here. So we're basically just trying to see how much a bass tone affects the higher frequency and the mid frequency tones. And this test clearly shows you just how close excursion is tied to amplitude and Doppler distortion in the mid to high frequencies. This graphic up here shows the amplitude distortion in red, and then it's also going to show the Doppler distortion, and that's covered by the blue, gray, and black. The black and the gray are the components that make up the Doppler distortion. Now, if you go back to that screenshot that I provided briefly a second ago, or follow the link to Klippel's, I said white paper, it's actually a presentation. Now, if you look at this screenshot from Klippel's presentation, I'm basically paraphrasing, but essentially what it says to me is that amplitude modulation is detectable at about 3%. 3% would be negative 30 dB down in amplitude. They state that Doppler distortion is at about 20 dB higher than that, so about negative 10 dB down. And that's where those thresholds of distortion are going to come into play. Now, at this particular voltage, because I'm only showing one voltage in this actual pane, those all run together, so it's really hard to tell what's contributing to what, other than the fact that we know, based on what I said earlier, that amplitude modulation is easier to detect, so more than likely what you're hearing is from amplitude modulation, and then some, of course, influence from the Doppler distortion.
Okay, now that IMD testing is done, let's talk about multi-tone distortion. Harmonic distortion was one tone. IMD distortion, that's redundant, was two tones. Multi-tone distortion is multiple tones. Multiple tones. Multiple tones. Like, see, I just did. Those are three different tones that I just did. When you played multiple tones, you enact a lot of nonlinearities in the speaker system or the drivers themselves. And in doing so, you're able to highlight distortions that you wouldn't otherwise hear with just a harmonic distortion sweep or just intermodulated distortion. And in my opinion, if you're going to present one bit of evidence for distortion data that actually makes sense, then it's multi-tone distortion. And here I am being a hypocrite. I used to provide that up until about a year and a half ago. And I kind of just, nobody was looking at it. Nobody was ever commenting on it. I don't think people understood how to read it. And I didn't really do a good enough job of explaining it, I guess. So some of that's on me. And I just quit providing it. But with this most recent speaker test, when I hooked this thing up and was listening even in the near field, not very high volume, you could hear all sorts of graininess. Now that graininess isn't from harmonic distortion, and it's not from IMD, at least not singularly. It's from multiple tones being played at the same time. Multiple tones is what music is made up of. Music is a whole bunch of sine waves, a whole bunch of tones played at one time. And I guess you could play square waves if you wanted to. Synth, I love synth music, but understand what I'm saying when I say that music is just tones. It's what it is. It's just made up of tones, different frequencies, different harmonics. An instrument has a fundamental frequency and it has its own harmonic profile. That's why a bassoon sounds different than a bass. That's why a flute sounds different than a clarinet. You could play the same fundamental tone, but the harmonics are different. And when you play back music, you're playing vocals, you're playing instruments, you're playing synthesized stuff, you're playing a lot of different things at one time. And that's what makes things get more distorted from a real speaker. And so, because of this listening test that I did last night, I decided, you know what, man? I need to start doing that again. And I thought, if I'm going to do that again, I need to make a video explaining why I'm doing that. And that's this video. Basically, this entire video is predicated on me providing multi-tone distortion testing again, because in my opinion, that is the quintessential testing that needs to be provided for a loudspeaker. Harmonic distortion is good for some reasons. Intermod distortion is good for some reasons. But multi-tone distortion simulates music. It provides you with complex series of tones, and it gives you a more real-world understanding of how the speaker is going to react in terms of distortion and in terms of compression. Now keep in mind the compression that you're going to see in this data test is going to be different than the compression that I already provided. And if I need to, I'll make a separate video for that, but hopefully for right now, that's good enough. So what I'm going to do is I'm actually going to run this multi-tone distortion testing 3 different times. The first time is going to be full bandwidth, 20 hertz to 20 kilohertz. The second time is going to be 100 hertz to 20 kilohertz. And then the third time is going to be 200 hertz to 20 kilohertz. Now you may be thinking, Erin, why are you doing this 3 different times? Think about it like this. You know that when you high pass a bookshelf speaker to a subwoofer, you relieve the strain from that bookshelf speaker. It doesn't have to play low frequencies anymore. And you probably know from experience that when you do that, you can increase the volume and have more output from that speaker with less distortion. Now, that's basically what I'm trying to emulate in this test, is a high pass filter. Depending on what I'm testing, I'll probably change the filter. I may stick at 80 hertz, I don't know. But for this particular speaker, being a full range speaker, 3-inch surface area, I'll let you try to figure out what it is if I'm not already showing it here. I wanted to see what happens if I let it play full band, cut it off at 100 hertz, and then do another test, cutting it off at 200 hertz. So what I want you to do, and what I expect you're going to need to do, is listen to each of these 3 different tests, but then go back and forth between them. Try to compare the highest output, which is going to be around 22 volts, between the 3 different tests. And I'll screenshot at the end the difference in all of those. So I'll show you what the distortion looks like and what the compression looks like compared between the 3 different sets at the highest output volume. And you'll see that it is different. And you'll think to yourself, well, why is it different, right? Because if you're only concerning yourself with the distortion in the vocal region, what you would expect then is that that's not going to change regardless of whether or not I play low frequencies or not. But remember, this isn't one-tone distortion testing. This is multi-tone. So if I'm not asking the speaker to play down to 20 hertz or 50 hertz, then there's going to be less distortion in the mid-range and the high frequency. And I know that may sound weird, but you'll see the data and you'll understand what I mean. And then you'll understand why multi-tone distortion testing is, like, in my opinion, it's light years beyond harmonic distortion. And that's why I'm going to start doing that testing again, because it's important to do. And anyway, that's kind of enough rambling from me. Let me run those 3 tests, and then we'll talk about the results, and then we'll go on.
I've already skipped to the end of this first test result because I want to show you what you're looking at here. On the bottom is the distortion. Okay, and this is relative to the fundamental. When something says relative to the fundamental, that's why you have negative values rather than percent. I like using relative to the fundamental because percent sometimes can jump off the scale pretty quickly, and it's hard to tell the difference between 1% and 50%. So when you use relative to the fundamental, it's easier to tell these differences. And this is a good case for where relative is easier to show than percentage scale. Okay. The black line represents the noise floor in the room. And this is important because as you get lower in frequency, the output of this speaker is low. Its roll off is at around 150 hertz or so. And so that means that the output of the speaker is not easily able to overcome the just regular old ambient noise of a static room. Even if there's nothing going on in the room itself, the room has a noise floor, and the lower in frequency you go, the higher that noise floor is. So at some point on the lower end, the results are kind of, I would say they're basically inaccurate if I'm being honest. But as long as you understand that, then you can still know how to use the data. And I would say, generally speaking, above about 50 hertz, you're okay to use that data. Okay. So then the gray lines represent each voltage that has been tested. And then the green line represents the last voltage that's been tested. So when it gets to this final 22.47 right here, That's this right there. And this is showing us that the last voltage tested 22.47, so that's 96 dB output, I should say, at 1 meter is about negative 10 dB down in terms of distortion. Well, that's really, really high. You're definitely going to hear that. This one is 8.32 volts, 3.07 volts, 1.13 volts. So 70 dB, 78 dB, 86, 87, something like that dB, and then 96 dB. Now, if we go up here, this is compression, and this shows us how much output we are losing as we increase the volume. And this is all relative to the initial output voltage or output SPL. So notice you only have 3 lines here, right? You have the green one and then 2 grays. Why don't you have 4 grays like you did down here? Because the first gray is your baseline. That's basically this flat gray bar right through here. So the other voltages are referenced to this initial voltage right there. Everything is referenced to 70 dB. As you increase from 70 dB to 96 dB, well, according to this data, you've lost 3 dB in compression. I know that the results right here say negative down here, but the way that this particular data is represented, a positive is a loss in output. So you have lost about 3 actually to 4 dB of output as you've increased the volume. So you wanted to be at 96 dB. Well, it turns out you were actually at around 93 to 92 dB because you've lost output due to some kind of compression issue, probably like heating of the voice coil or something along those lines. And again, I mentioned earlier that I think when I hear the graininess of sound, that's due to compression. And I recall reading that somewhere, but if I'm being honest, I don't recall where. So take that maybe for now with a grain of salt, but keep this information in mind. I'm about to play back the stimulus starting from the beginning. I'm going to speed it up so it doesn't quite take as long, but listen for how grainy the sound is as you get to this 3 volts, 8 volts, 22 volts. I'm telling you, you're going to be like, whoa. And it's going to be way more eye-opening than the harmonic distortion, and certainly even more eye-opening than the intermodulated distortion. So put your headphones on, turn the volume down a little bit, and let's go. Now let's compare the 96 dB output for each of the 3 multitone distortion tests. Again, those 3 are going to be full band, 20 hertz to 20 kilohertz in red, 100 hertz to 20 kilohertz in blue, and 200 hertz to 20 kilohertz in black. And what you notice right off the top is in red, the full band has higher distortion throughout. And if you bandpass this speaker from 200 hertz in black and above, then you have about negative 10 dB, which is about 33%, I believe, down to about negative 30 dB and maybe negative 25 dB. So I'm ballparking that at around 3% to about maybe 5% THD. So you lose a ton of distortion going from full band to band limited. If you were to put a subwoofer with this system, then you can see that you would save yourself a lot of distortion. But what happens when you talk about compression? Here we are. 0 dB references the lowest output. Anything above this is output that is lost. Same thing as before, 20 hertz to 20 kilohertz is in red, and then the other colors represent the other tests. In red, you lose about 3 to 4 dB, depending on what frequency you're talking about. But if you band limit this speaker, you save some output. So you actually only lose about 2 dB to 3 dB. And when I say only lose, well, that's not a little bit, but you do see that you save some compression by band limiting this speaker. So you save compression, you save distortion by band limiting the speaker. But more importantly, I think this data tells us don't play the speaker that loud. And I think anybody realistically already knows that. Now, just to recap, I'm going to play these 3 sound clips back to back so you can hear what they sound like all in a row and save you some time from having to scroll all the way to the back.
That's it for this video. What I hope is that you've learned something from it. Now, what I encourage you to do is to ask any questions if you have them. I'm going to try to drop a bunch of links in the description below to various sources from Clipple, the one I mentioned from Purify as well. And what I may do if I have enough interest is I may just do a live stream sometime soon and we can talk in real time about this video, because I understand that it's complex, and trust me, it gets a lot more complex because the stuff that I've learned in the last decade, I don't even remember half of it. I'd be lucky if I remember like 1/20th of it. And a lot of that goes a long way toward explaining the different distortion elements, the nonlinearity. So if the suspension isn't uniform in versus out, if the motor force isn't uniform in versus out through excursion, that creeps up in different forms and at different frequencies depending on the speaker itself. So a large woofer may behave differently than a small mid-range. And all of this stuff matters. The devil really is in the details. But my hope is between just a basic harmonic distortion sweep to give you an idea of how low you can take a driver, and the multi-tone distortion, which will give you an idea of the contributing factors toward maybe high distortion and when you can expect the speaker to start sounding really grainy and have an idea of how loud you can turn it up. Between all of that, you'll be better informed and you'll better understand this topic itself rather than just saying, yeah, it's high distortion. Like I said, if you have any questions, please ask in the comments below. I apologize if you feel like this video is taking too long, but if you want to learn, that's what I'm trying to do. Is I'm trying to help you learn, trying to help teach, and I'm trying to teach myself at the same time. And as a community, we will all grow in our learning and our understanding. And these won't be just numbers that somebody put up on a website. These will actually make sense and mean something to us. And that's important because the data is important. I don't do this stuff trivially. And I truly believe that having more information is much better than just having me say, it doesn't get loud. That's useless. So with that all said, yes, I appreciate you watching. If you have any questions, let me know. And if you're interested in a live stream sometime, let me know. Try to do that sometime soon. Talk about this stuff. And maybe I can try to have some guests on that are well more versed in these different distortion types and the reasons for them at some point in the future. But for now, hopefully this is good enough. Gives you a good idea of what the distortions sound like and how to track it in the measurements. And I will talk to you all later. Take care. Peace. It's really hot in this garage. I got to turn the AC on. Later, y'all. If you're thinking to yourself, you chose the worst possible speaker to do this with, why would you push this little speaker to such high levels? Well, that's actually the point. That's exactly why I'm using this speaker. When I listen to it within like a meter, so like 3 feet, just a regular old pair of speakers, I started to hear compression. I started to hear that grainy sound that I often attribute to compression. And that's what triggered me into thinking I need to do some additional testing of the speaker, and then I need to do a video to explain what that data means. And then I thought, man, I need to start doing this again for future speakers. So while I don't think that I would necessarily push such a speaker to the limits that maybe I'm going to show you in this video, I can say that to some degree, I actually did. And that really matters when you're talking about listening at different distances. So here's the thing. When somebody says a certain volume level, so they say 80 dB, that number is meaningless unless they tell you how far away they are from the speaker. 80 dB at a few feet away is going to sound a lot louder to you than it would be if you are 10 feet away. Because the further you get away from that speaker, the less loud it's going to seem. You already know this. Every doubling of distance drops the amplitude by about 6 dB. And depending on which source you read and depending on what frequency range you're talking about, research shows that our perception of output doubles in terms of it sounds twice as loud between 6 to 10 dB of volume increase. So if I take the volume from 80 to 90 dB, then it sounds twice as loud. Conversely, if I take it from 80 to 70 dB, then it sounds half as loud. Now, if I move from maybe a foot away to 3 feet away or a little bit further, well, that's going to drop the volume level, or the SPL level, a lot. So it could sound half as loud. That's what matters. If you're listening close, you don't have to turn up the volume as loud as you do when you're listening further away. So when some person says, I listen to 80 dB, and you're saying, well, I do too, but I'm having these issues. Well, you may be listening to different distances. Number one, that could be a problem. So when I talk about running these tests at X volume, I'll always specify at 1 meter or however far away, because that's important. If you're at 1 meter away and then you go 2 meters away, so roughly 6 feet, then you drop the volume by 6 dB. So it's almost not quite as loud or not twice as loud anymore. Just keep that in mind. I see this come up a lot, and I think a lot of people don't quite understand the significance of not just volume, but volume and distance. Those should always, always, always be paired together, because one number is useless without the other.